And today in this video we'll be discussing the second module of 18CS42. Okay, so in this module we have two topics mainly, which is divide and conquer and decrease and conquer. So this is the new method which we'll be learning, by using which we can design algorithms. Okay, first we'll be learning, in the first part we'll be learning what is the algorithm, and in the second part we'll be looking at its applications. Okay, in the real life, what are the applications. In the third part we'll be looking at the second approach, which is decrease and conquer. Okay, we'll be looking at the advantages and disadvantages. So before moving on, if you like this video, hit the like button and don't forget to subscribe to my channel. Okay, so let's move on to the first topic. In the first topic we are discussing the general method, what is divide and conquer. See here, if there is a problem of size n, what we'll be doing is we'll be dividing into half parts. Okay, so it will be sub problem of size n by 2, and if it's needed to be solved more, we'll be dividing into n by 4 and n by 4. Okay, so like that we are dividing the bigger problem into smaller modules and smaller modules. Okay, so when it becomes small enough that we can solve it directly, we will solve it directly, and each solution will combine to get the upper position, and finally we'll combine to get the final solution. Okay, so that's what we do in the divide and conquer. It has two parts. First we'll divide the problem, and then after dividing it we'll conquer it. Okay, means we'll find the solution to the main problem. Okay, so that's the general method. And control abstraction is just the written algorithm. So here it's nothing but if small p means if the problem becomes such small that it can be solved by using a method, it should be solved, else it should be divided into smaller parts. Okay, like p1 p2 till pk. Okay, so after dividing into small parts, then we have to apply divide and conquer to each part. Okay, we'll be applying the divide and conquer to each part and finding out the solutions. Finally we'll combine all the solutions together and return the main solution. Okay, so this is the algorithm which we write here as divide and conquer. Okay, the second topic is recurrence equation for divide and conquer. Okay, so when we divide the main problem into smaller parts, each of these smaller part will be solved parallelly, and they will have a similar solution. Okay, so we'll be using the same technique which we used for the bigger problem in the smaller problems also. Okay, so the time taken will be g of n if it's smaller, means if it reaches a level where it can't be divided anymore, that problem we should be solving, that how much time it takes g of n time. Okay, and if it's not that much small which can be solved directly, then we have to divide the problem, right? So it will be divided into t of n n1, t of n2, t of n3 t of n3 till t of nk. Okay, plus f of n for comparisons. So basically what we are doing is we are calculating the time taken for each of these iterations, plus how much time will be taken for returning the statements. Okay, so we'll be combining all this time taken to get the final time taken for the main problem. Okay, to calculate that total time taken, we have two methods. First one is substitution method. Yeah, this we looked in the last module also. The substitution method means what we'll be doing is, see here, if t of n is given as t of n minus 1 plus c. Okay, so what will be t of n minus 1? T of n minus 1 will be, substitute here t of n minus 1, then here it will be t of n minus 2. Okay, plus c. Then what we are doing, we are substituting this value here. Okay, so we'll be writing t of n minus 2 plus c in the place of this. So it will be t of n minus 2 plus c plus c. Like that we are substituting till k, and then we'll be finding out the main solution. Okay, that we had discussed in a lot detail in the previous module. Okay, so in this module we'll be learning about the second algorithm, which is master's theorem. Okay, this is a very easy theorem, and we can solve very tough problems within a very small amount of time. Examples to give you a clear picture of what the theorem is. Okay, so mainly the problem will be divided into b instances, means c. Suppose that this is the main problem n. Okay, I'll be dividing into 4 instances, n by b 4 times. Okay, so what will be the value of b? It will be n by 4. Okay, b will be 4. So if I divide 4 times, if I combine all of these solutions, it will be n finally, right? So first our first step is to divide the problem into b instances, and a needs to be solved. Okay, a needs to be solved by recursion. So suppose that when we divide into many problems, one of the problem takes direct solution, means it becomes very small problem and we can solve it directly. So how many problems are needed to be solved by recursion? That is the a, means in this case if it's directly solved here, the remaining ones will be solved by recursion. Okay, so this will be 3. Okay, so remember what is a and b very clearly. Okay, now after getting that, we can define the t of n as t of 1 means if it's small we can directly solve if n is 1, or else we have to solve by a into t of n by b plus f of n. A means how many problems are needed to be solved by t of n by b, means recursion. Okay, by recursion a number of problems will be solved plus f of n for the calculation of return statement and comparison. Okay, this can be taken as n or n square, and it depends on the problem. Okay, so after this, after knowing this main formula, you'll be using this in Master's theorem. Okay, so basically what the Master's theorem says, you have to remember these three things. Okay, f of n can be taken as n power d. Okay, if they give you in the question a t of n by 2 plus n square, so what will be the value of d here? It will be 2. Okay, so like that we have to find out what is d according to the question which they have given. Okay, after finding out d, a and b will be visible by the question, means a will be given as 2t or 3t, like that. Okay, so a and b we have to find, and the d we have to find. Okay, after knowing a, b and d, we have to compare the three cases. Okay, which case it fits, then we have to find out a is less than b power d or not. So in this case a is equal to 3. Suppose that a is equal to 3 and b is equal to 2. Okay, b is equal to 2 and d is equal to 2, n square, right? So d is equal to 2. Now what is a? A is 3. B power d means 2 power 2, 4. 3 is less than 4. So which case it falls? It falls in the first case. So what will be the time complexity? N power d. What is n power d? N power 2. So it will be the order of n square. See how easily we found the final answer. Okay, so in that way we'll be finding out the tn by using the a, b and d values and finding out which case it falls in and writing the final answer. Okay, so let's see it by an example. Okay, so see, this is the example here. In this example, first we'll try to solve by the substitution method. Okay, and after that we'll solve by the master method. Okay, so see here, in substitution method t of n is given to be 2 times t of n by 2 plus n. Okay, so t of n is given here, we'll be writing here first, then in the second one we'll be writing what is t of n by 2. Substitute n by 2 here, so we'll be getting 2 times t of n by 4 plus n by 2. Okay, and here what is t of n by 4? If you write t of n by 4, it will be t of n by 8, 2 times t of n by 8 plus n by 4. Okay, so what we'll be doing is we'll be substituting t of n by 4 value, this whole value, in the place of this one. Okay, after doing that we'll be obtaining this equation t of n by 2 as this one. Okay, and t of n by 2 value will be substituting in first equation here. Okay, after substituting that value we'll be obtaining a general equation as 8 times t of n by 8 plus 2n plus n, which is 3n. Now can you observe a pattern here? See, t of n is 2 cube t of n by 2 cube plus 3n. Okay, so generally we can write as, if it's extended to k terms, t of n is equal to 2 power k into t by 2 power k plus kn. See, here it was 2 cube, so we wrote 3, so 2 power k will write kn. Okay, after writing that, then we are given that t of 1 is equal to 2. What does t of 1 means? T of 1 means n should be equal to 2 of k. So when we consider n is equal to 2 of k, then what we will be obtaining is 2 power k t of 2 power k by 2 power k. What is 2 power k by 2 power k? It's 1. So t of 1 is given as 2. So we'll be writing 2 here, and 2 into 2 power k into 2 is 2 power k plus 1 plus kn from here. Now n is equal to 2 power k. Take log on both sides, you will get the value of k as log n, right? Then substitute the value of k as log n. Okay, after taking n as common, substitute the value of k as log n, and what's the order? Order is n log n. See, n from here, and 2 is the constant, so we can ignore here, and log n is remaining, so n to log n. That's the order. Now see by master's method how easy it is. See, what's the value of a here? 2. What's the value of b? 2. And n power d is 1, means d is 1. When we get a, b and d, what we have to compare is a less than or equal to or greater than b power d. B power d means 2 power 1. Okay, 2 power 1. So it will be 2. What is a? A is given to be 2. So a is equal to b power d. So what's the case here? Is the second case, right? See here is the second case. Okay, see, a is equal to b power d. At that time what the answer should be? N power d log n. Okay, remember, n power d log n. So we'll be writing here n power d log n. Okay, n power d means 1, n power 1, and log n we'll be writing here only. So it's the order of n log n. See, within one step we got the final answer. This is the same answer as the previous one. Okay, So we use master's method to find out the answer quickly, okay, by direct formula. Looking at the applications of divide and conquer, the best example is binary search. In binary search, how we'll be doing is we'll be dividing the array into two parts. Suppose that in binary search the array's elements are sorted. So first, if this is the element to be found, what we'll be doing is we'll be considering from the middle part. Is the element behind or ahead of the middle part. So by doing that, we'll be knowing where the element lies. So in this half it lies. So we'll be considering only this half. Then we are again dividing into two parts. We'll be dividing till we get the final answer at the mid position. Okay. So this is the divide and conquer algorithm. So the recursive binary search algorithm will be as follows. Okay. To write the algorithm, first you have to write what's the input. Input will be taking an array. Okay. Normal array of n elements which are sorted, and search element key means we are taking an array of n elements, and which key we have to find out, which element we have to find out. These two things will be the input. Okay. And output will be return 1 if key is found, else 0. If the element is present, we will return 1, or else we will return 0. Okay. So these are the outputs. We will proceed only if low is greater than less than or equal to high. Okay. See, initially low will be this one. Okay. First position will be low, means 0, and n minus 1 will be high. Okay. So when we have low less than high means we are under this domain, then only we can search the element. Okay. After that, what we'll be doing is we'll be finding mid. What does mid mean? Mid is equal to L plus h by 2. So L plus h by 2 will give us the mid position. Okay. After getting the mid position, we have to compare if the element lies in the left part or in the right part. So for that, what we'll be doing is, see here, firstly we will be checking if key is equal to a of mid. If the mid position has the element which we need to find, then we will return 1. Else we have to search if the key is in the left part or in the right part. If it's the left part, means key is less than a of mid. A of mid is this value. If you have to search this value, if it is in the left part, then what we will do, return binary search. We will call again this algorithm, and a of low till mid minus 1 comma key. See what we are doing, a of low till mid minus 1. What is low of till mid minus 1? This is low, and mid minus 1 means this. So in this algorithm we are just passing this array, this much array. Okay, this we are not passing, and the key we are passing. Else in other case, if it's higher than the algorithm, if it's higher than the key, means this a of mid, and the key to be find out is higher than the mid part, then what we'll be doing is we'll be passing this array. This array means the low part will be mid and high will be this. Okay. So mid plus 1 and high. It's not mid, actually it's mid plus 1. Okay. Mid plus 1 and high. So the second half of the array will be passed. Okay. This one. This is the whole array. This is the mid part, and the second half will be passed to the binary search. Again the same thing will happen. The array will be divided again, and mid part will be here, and the key will be searched if it's lying here or here. Okay. So like that we are dividing the algorithm, and finally when we get the answer, we are returning the value if it's 0 or 1. If we get, we return 1, else at last if we till last if we didn't get, we'll return here as 0. Okay. Let's look at the time complexity. First, the input parameter is n, and basic operation is comparison. We are in each iteration we are comparing if key is equal to a of mid. Okay. So the basic operation is comparison, and the input is n. Now number of comparisons made means depending on the position of the key. If the key is found to be at the first position, means it's in the middle position, the first iteration only will get the answer, right? So t of n will be 1. That's the best case. In the worst case, if it's not found out, means till last also it's not found out, we'll be dividing how many times? Log n times. See, I'll be giving you an example. See here, if you have 8 elements, okay, consider 8 elements, then we will be dividing in two parts, 4 and 4. Again we will be dividing in two parts, 2 and 2. Then finally we will be dividing into one part. Okay, 1 1 1 1 1 1 1 1. Now see what's the level. First iteration we divide into 2 parts, second iteration we divide into 4 parts, third one at last we divide into 8 parts. See, 8 elements were there. For that we required 3 levels. So what does that mean? 8 can be written as 2 cube, right? So how many powers will be there? That much levels will be there, right? So how many iterations will be there? The number of levels will be the number of iterations. So how we will get that? 2 power 3. So by considering the log base to n, okay, n means number of elements, okay, that is x. Okay, now see, n is the number of elements. In this array I considered 8 elements, right? So when we find out the log, if we can write here as 8, what is log 8 base 2? That is equal to 3. Okay, so here we'll be getting 3 times, it will be calling the same function. Okay, so 3 levels. So in that way we'll get the value O of log n, means how many times it's called. Log n we got there as 3, right? So 3 times the function will be called in the worst case, because till the last level we don't get the element. That's why 3 levels are there. Okay, and that's the time complexity of the algorithm. Under this topic we'll be discussing how to find the maximum and the minimum element in an array. Okay, so if this is the given array and it has just one element, okay, so suppose that it has just one element, this is the array. So at that time the minimum and the maximum will be 1 if L is equal to H. L means the lower bound, H means the upper bound. If both are the same, if only one element is there. So suppose that in the second case, if there are two elements, if L is equal to H minus 1, L is this, H is this, H minus 1 will be L. So if there are two elements, L will be equal to H minus 1. If this is greater, this will be the max, and if this is greater, this will be the max. And similarly for min also, if this is smaller, this will be the min, or else this will be the min. Okay, so this is for the two elements. If there are multiple elements, what we'll be doing is we'll be dividing this array into two parts, and again we'll be doing the same thing. If there are still multiple elements, we'll be dividing into two parts, so that in a particular case we'll reach where only two elements or one element will be there. In that case we'll be returning which is the maximum and the minimum element. So when we return that, see here, when we return that, at that time we'll be comparing with this also. See, to be clear, what I mean is, see here, if this is the array here, okay, and we have divided into two parts. Okay, suppose that it has two elements, here also it has two elements. Okay, now we'll be finding out the maximum and the minimum element. So let's take some values. So if you consider values 74, 94, 78, 91 and 82, in that this is the maximum and this is the minimum. Okay, and here this is the maximum and this is the minimum. Now what we'll be doing is we'll be comparing this maximum with this maximum, and what maximum we'll get will be returning in the main array. So 94 we get the maximum, and the minimum will be compared, and that minimum will be returned, which is 78 in this case. So in that case we'll get the main element here. If this was also divided, at that time it has some upper bound here, right? So at that time we'll be comparing the maximum among these two and the minimum among these two. Okay, so that will be returning those maximum and minimum. So finally at the top we will get maximum and minimum among all these elements. Okay, so what we are doing, quickly recap, we are dividing the array into many parts and finding out the maximum and the minimum among each part, and then comparing and returning the maximum and minimum, and again comparing till we reach the top position. Okay, at the top position we'll be having the maximum among all these and the minimum among all these. Okay, so this is the divide and conquer rule for finding the maximum and minimum element. Okay, so these are the two functions wherein we'll divide the array into two parts and we'll be returning the max and minimum. Here we'll compare the max with the max and min with the min. Okay, so we'll be returning which is more max, and which will be returning the least minimum element. Okay, and the time analysis will be, see here, what will be the input. Input is the number of elements between the I and j. Okay, so if this is the I first position and j is the last position, so between I and j how many elements are there? N. So that will be the input parameter, and the comparisons will be 3. First one for a of I and j, and second is for max, and third is for minimum. Okay, after that we'll be having the greater the value of n, the greater the divisions will be. Okay, so the time complexity will be same, means there is no best case and average case, and it will be just the same case. Okay, if there are variations, means in the sorting, right, see in the sorting it depends on the position of the element. No matter how much big the array is, it still depends on the position of the element in the array. So that that's known as variation, but in this case only n matters. Okay, wherever the thing is, means wherever the element is, we'll be still dividing the array into least parts. Okay, so in this case the time complexity will be 0 when n is 1, 1 if n is 2. See, n is 1 means we just get the position in the first iteration only, so t of n will be 0. If it's 1 if n of elements is 2, because one comparison will be made, so n will be t of n will be 1 when n is 2. Else if n is greater than 2, we'll be dividing the array, right? So it will be t of n by 2 plus t of n by 2 plus any constant value here. Okay, for the comparison purpose. So the time complexity will be written as 2 times t of n by 2 plus 2. By using the Master's theorem, we can write the value which is theta of n. T of n will be theta of n, which means it's a linear growth. Okay, the more number of elements, the time complexity will be more. Okay, coming to merge sort, there are two steps. First one is splitting the array and then merging the array. Okay, in splitting the array we'll use merge sort algorithm. In joining the array we'll use merge algorithm. Okay, so two algorithms for this particular problem. So consider this example. In the first place, what we'll do, we'll find out the mid position and divide into two parts. Similarly, we'll divide here also till we obtain the 2 digits or 1 digit. Okay, after that we'll have to combine the elements. How we'll combine? We'll compare 8 with 2. If 2 is less, it will be placed first, then the next element will be placed. So 1 will be brought from here only, and then again we'll compare these both. So in these both, what we'll be doing, we'll be starting from left side. 2 and 1 will be compared. Which is smaller? 1. That will be placed here, and then 2 will be placed here and 8 will be placed here. Similarly, here also we'll be doing the same thing parallelly, and 4, 9 and 3, right? So among 4 and 9, 4 will be placed here, 9 will be placed here. When 3 is there, 3 will be placed first, 4 then 9. Okay, in the similar way we'll compare at last 1 and 3. Which is smaller? 1. So next 2 and 3. Which is smaller? 2. Then 8 and 3. 3 is smaller, so 3 will be placed. Then 8 and 4. 4 is smaller. 8 and 9. 8 is smaller, so this array is over, then 9 will be placed here. Okay, so this is the algorithm for merge sort. So we have two algorithms. First one is for splitting. In splitting, what we will do, first, if n is greater than 1, we will be splitting into two parts. Okay, 0 to n by 2 and n by 2 plus 1 to n minus 1. That means if this is the array, n by 2 is this position, so 0 to n by 2 will be here, n by 2 plus 1 till n, this is the array. Okay, so again we'll be doing the same thing. We'll be calling the same function, merge sort. So in this case, n by 2 will be here, and n by 2 plus 1 till n will be here. Okay, so that will be doing till we get either 2 or 1 element. Okay, so we are calling the merge sort 2 times. Okay, for each half. Then after that we are using merge sort. Okay, after reaching this position, we'll be using merge sort. For what we'll use merge sort? For merging the elements present here. Okay, so 8 and 2 is getting compared, and 2 and 8 is written here. So for that, the algorithm will be, see here, the input will be b of 0 to n minus 1, c of q 0 to q minus 1, and a of means this is the main element where we have to place. So we'll get two half elements in the merge. See here, two half elements means this one sub array, this one sub array. So this is b and this is c. Okay, see, this is b and c. These two elements, which are 8 and 2, will get this, and we'll be placing the final one here. So what we'll be doing is, first we'll compare I with p and j with q. I is the first position here and j is the first position here. So we'll be comparing the first position. Since we have only one element, we'll be comparing 8 and 2. Which is smaller? 2. So in case I is smaller, at that time b of I will be placed in a of k. What is b of I? B of I is the first position of B array, which is 8. Okay, or else 2 of this array, which is j. Okay, so what we'll be doing, C of j will be placed in A of k, or B of I will be placed in A of k. K will be starting from 0. So this is the A array. We'll have the elements here. K will be first 0, then 1. Okay, so we'll be comparing I is smaller or j is smaller. In this case, j will be smaller, so C of k will be placed here, and then b of I will be placed here. Okay, so that's what we are doing. See, if b of I is smaller than c of j, then in a of k, b of I will be placed. If 8 was smaller than 2, 8 would have been placed in a of k. Else, see here, since 2 is smaller than 8, a of k will have c of j. C of j was what? C of j was 2, right? So 2 will be placed in a of k. Like that only we'll be keep on doing until we reach the final position. Then we'll copy the b part in the a part if the array is over. See, what this code does is, if there is an array here and two arrays, okay, So one has 3 elements and one has only 1 element. Okay, 3 elements and 1 element. So we'll be comparing each element with this, and if this element gets over, at that time this whole array should be placed here. So suppose that this was the least element, it was placed here. Okay, then the remaining one should be copied, right? This all 3 elements should be copied here without any more comparisons. So for that, when the array is over, at that time we'll copy the remaining elements. Okay, it depends. If I is over first, we'll copy this, or else if j is copied first, if j is over first, we'll copy the remaining elements here. Okay, coming to time analysis of merge sort, in that we'll have the input parameter as n, basic operation is the comparison, and merging has two parts, right? First one will be splitting, second one will be combining. Okay, so for that we will be splitting two parts, so it will be n by 2 plus n by 2, and for merging it will be n, because we are just comparing the elements and merging it. Okay, we are not dividing any further. So the t of n formula will be 2 times t of n by 2 plus cn, and we will be finding a, b and d, and finding out the time complexity by using merge master's theorem. Okay, so it will be n log n. Observe here very carefully. In quick sort, we are selecting a pivot element, and by using that element we are swiping the other values. Okay, so firstly, if this is the array, we can consider any element as pivot element. Okay, what does that element do? Suppose that the pivot element is p, which is 14. Okay, so first we'll be comparing, we'll be starting from, if this is L, we'll be starting from L plus 1, next element of pivot element, and compare it with the last element. Okay, so what we'll be doing in the first step is, we have to find out the element which is greater than 14 after this position, which is 15 will get here. Okay, and from the last position we'll find the element which is less than 14, so we'll get in the first iteration only 11. When we get that element which is less than 14 from left and less than 14 from right and greater than 14 from left, we'll stop at both position and swap those values. Okay, when we swap it, we'll get the values as 11 here and 15 here. Next, we'll increment this and decrement this. Okay, so we'll compare 12 and 16. So from left, what should be the case? It should be greater than 14. 16 is greater than 14, and from the right, 12, which is less than 14. So we'll swap 16 and 12. So in the third iteration, we'll have 12 here and 16 here. Next, we'll increment this and decrement this. Next, from here, from left, what's the case? It should be greater than 14, which is 17. It's true. And it should, and from the right, it should be less than 14, which is 13. It's true. So at that time, we'll swap both these values, and then we'll have the values 13 and 17 here. After that, we can't swap anymore, because we were decreasing from here and increasing from here. Now at this time, this crossed here, right? See, if you consider L, which was moving from here and till here, when we reach, L is now here in 17, and from here, if it was H, if we are considering H from here, it was decreasing, and now H is before L. H is in 13 now. Okay, so in that case, L is after H, right? We can't consider in this case. Okay, L should be less than H. Okay, so in this case, there will be no more swapping, and 14 will be placed in H position with 13. Okay, it will be exchanged with 13, so H will be placed here. Okay, so that's the middle position, pivot position. Okay, so this is P. Now that was our first step. In to quickly recap, what we did is, we can consider any element as pivot element, and after that we'll start from here L, and we'll start from here H. Okay, we'll increase the element from here, and we'll compare each element. Is 15 greater than 14? From the left it should be greater. Okay, so 15 is greater, and from the right it should be smaller. It is smaller than 14, which is 11. If it's true for both the cases, and L is less than H, H is this and L is this. Okay, so it's less than H, so we'll swap both these values. So after that, when we swap, we'll have 11 here and 15 here. Then we'll increase L and decrease H. Okay, so now L is in the 16 and H is in the 12. Okay, so after that, we'll swap both of these, because 16 is greater than 14 and 12 is less than 14. Okay, so when we swap, we'll have this position, and then we'll compare 7 and 13, and we'll swap it, and we'll have 13 here. See, we decreased H here, so now H is placed in 13, and we are increasing L here. Now L is in 17. When H becomes less than L, at that time we'll perform no more swaps, and we'll exchange the position of H with the pivot value. Okay, so 13 will be placed in the pivot value, which is 14. So 13 is here, and 14 will be placed in the h value, which is in the place of 13. Okay, so what does this mean? This means that when we sort the elements, see, these are all the elements, right? When we sort it in the increasing order, 14th sorted position is this only. See, 14 is the fourth largest element among these all elements, right? See, 13, 11 and 12, these can be shuffled here and these can be shuffled here, but 14th position is correct here, right? When we get one position which is correct, then we'll perform the divide and conquer. Okay, so our first step is over. Now coming to the second step, we'll divide the array into two parts. Again, we'll do the same thing. We'll consider the element of we'll consider the any element as pivot element, and then we'll be comparing from left the greater element, and from the right, which is lesser element. So we'll be comparing for each of these. We'll be finding the sorted position for the pivot element, and again we'll be dividing the array till we reach all the sorted position, like how we found for this, right? We'll find the sorted position for all of these individual elements. Okay, after finding all of those individual elements, we'll be combining to the main array. Okay, now let's see how to do that. Since we get finally many elements which are sorted in the main position, at that time we'll combine all of these elements by using return statement in the final array, which will be sorted. Okay, because each of these element, what we found, the sorted position by using pivot value, we found the sorted position for each of these element. Okay, so in that way we'll combine all these sorted position to get the sorted array. Okay, let's go through quickly through this algorithm. Okay, so what's the input is the orderable array, means any array, normal array, and the output will be the sorted array. Okay, so in first position, what we'll do, if L is less than H, as I told you, L is starting position, H is the ending position, so L should be less than H. At that time only sorting should happen. P returns the partition of L comma H. This means that this is the second algorithm. So this is the pivot position of the main array which we found here, that will be returned by this algorithm. We'll be looking at this algorithm after this. Okay, so when we return the position P in the previous case, which we got 14, after that what we did, we divided the left part and the right part, and each part we will be doing the same thing. So I'll be calling quick sort for A of L till P minus 1, means this is P, so P minus 1 will be here, so this is the last position, and L will be here, and the second half will be P plus 1, which is P plus 1 will be the next position of this, and till H. Okay, so we'll be calling quick sort for both of these. Now let's see what is the algorithm for partition. How we'll be finding the 14th position? For that, what we'll be doing is, we'll be considering L and H first and last position, and P will be assigned as A of L, means pivot element will be the first element here. Okay, after that I will be starting from L plus 1, means I will be starting from here, and J will be starting from last position. What we did was, while I is less than J, I should be less than J, till then only swapping will happen. If I is greater than J, at that time swapping won't happen, means if I crosses J, okay, at that time swapping should stop. While A of I is less than P, P is this one, and A of I means this. Okay, while it is less, we have to find the greater element, right, from the left. So whenever it is less, I should be incremented. Okay, whenever we find the greater element, at that time we'll stop I. Okay, if you find the greater element in the first position, I will be stopped here. Then similarly, while A of J is greater than P is this one, consider this as 14, and from the H we'll be comparing. While A of J is greater than P, means if A of J means this one, this position is greater than P, this should be less than P, because from right when we are comparing, this element should be less than P, which is 14 here. Okay, so whenever we get the greater element, we should still move on further. When we get the element which is less than 14, at that time we should stop. We'll swap A of I and A of J, like last time we did, right? In the last example, we got here as 15 and here as 11. So we got 15 and 11, we compared. 15 was greater than 11, so we should get greater element from the left and the lesser element from right. If that's true and I has not crossed J, at that time we'll swap the values. Okay, so we had swapped the 15 and 11, and we compared the next elements, means I was incremented, I became the next position, and J became the second last position, and we'll compare the same things. Till when we'll compare? Till I crosses J. Okay, while I is less than J, if I is less than J, this process will happen till we reach the middle element, and after we reach the middle element, we'll swap it with the pivot element. Okay, pivot element will come in the middle element, and the array will be divided into two parts. Okay, so this for this algorithm only we have to find out this position, and after finding the position, this will return the position. Okay, means the mid position will be returned, and after getting the mid position, we'll do the quick sort for each of this array. Okay, it will be done in two parts, and we'll perform the same thing for these both array. Okay, and we'll be keep on performing this till we get the all the sorted position, and we'll be combining at last by returning all these values, and we'll get the sorted array. Okay, coming to the time analysis, the input parameter is n, means the size of the array. What's the basic operation? It's the comparison. Okay, and there are two comparisons. First one is for a of I, and the second is for a of j. Okay, and there is variation of time for the same size of n, because if you have the sorted array, or if we have the pivot element in the first position, that time the complexity of the time will change. So let's look at the best case. Best case is when the pivot position is in the already in the sorted position. So if you consider the pivot element, if it's already in the sorted position, we need not perform the partition algorithm. We can just directly divide the array into two parts. Okay, so the best case will be when the pivot position is already in the sorted position. Okay, so that time the time complexity will be just dividing. So we'll be dividing, so t of n by 2 times plus c of n. C of n is the time taken for partitioning method. Okay, so for dividing, the time is cn, and for each of these individual times, to find the pivot position for each of these individual elements, the time will be t of n by 2 times for this one and for this one. Okay, so the t of n will be 2 times t of n by 2 plus c of n. By using the master's algorithm, we'll obtain the time complexity as O of n log n. Okay, the worst case is when the array elements are already in sorted order. It looks weird that if it's in the sorted order, why will that be the worst case? Let's look why it's true. See here, when the array elements are in sorted order, pivot element will be here, and how many comparisons will be made? It will be divided into two parts. Since this is in the sorted position, the left part will be empty, right part will have 5 elements more. Then again it will be divided into two parts, and it will be again divided into two parts. So what's the thing? In each iteration, one element is getting reduced. Okay, so if it was not in the sort order, it will have been reduced by 2 elements here and 2 elements here, and it will have all these elements divided into two parts. But in this case, the element is getting divided into n minus 1, like that it's getting divided. And as you can see, if you apply the substitution method and to calculate the t of n, at that time we'll get O of big O of n square, and as you know, the time complexity of n square is greater than n log n. So in this case, when the array elements are sorted in order, at that time we'll have the time complexity as more. Okay, to recap, what we did here is first see to calculate t of n, how we'll get t of n is equal to cn means the time taken for comparison and dividing. Okay, so cn plus t of n minus 1, time taken for this array's time will be the time taken for comparison plus t of n minus 1. If this is 5, n minus 1 will be 4, time taken for this will be cn plus time taken for cn minus 1. So in that way it's getting reduced. Okay, so that's how we got this equation, and by using substitution method, we'll be finding the time complexity. Okay, as we all know how to do the matrix multiplication. If you are given with two matrices, how we used to find out the third matrix, means product of two matrices. A of 1 1 will be multiplied with this, and we'll be adding that with the product of A12 and B21. Okay, in that same way we'll multiply this row and this column, and then this row and this column, this row and this column. So like that we'll multiply 8 times and add 4 times. See, first multiply, second multiply, like that 8 times will multiply, and addition will be done 4 times, first, second, third and fourth. Remember this, 8 times multiply and addition will be done 4 times. So Strassen's matrix multiplication will have a little bit less time complexity. Okay, when you find this time complexity, see here, in the traditional matrix multiplication, time complexity will be 8 times t of n by 2. 8 times it's for multiplication, and t of n by 2. See here, what's the order of this matrix? It's 2 by 2. Okay, 2 cross 2, right? So it's 8 times n by 2. N by 2 means if we divide into two parts, see here it will be 1 cross 1, each will be 1 cross 1, right? 1 cross 1, and this is getting multiplied with this one, this is getting multiplied with this one, then we are adding both of these. So in that case 8 times it's happening. See here we are dividing to 8 parts. Okay, so in that way the time complexity will be 8 times t of n by 2. Okay, 8 times t of n by 2. Applying the master's theorem, we'll get the time complexity as O of n cube. Okay, now let's see what the Strassen's method is. Here some things are there which you need to keep in mind. Remember these formulas. Okay, we have to find out what is p, q, r, s, t, u and v. Okay, after that we have to find the main array element, which is c11, c12, c21 and c22. This depends on these values. Okay, these values you have to find out by remembering these formulas. Okay, so as you can see in this formulas, you will multiply 7 times and add and subtract 18 times. This doesn't matter because adding and subtracting is considered as constant value. Okay, only multiplication will take more time. So basic operation here is multiplication. In the traditional method, the number of times you multiplied was 8, right? Here you are multiplying just 7 times, so it's reduced by a factor of 1. Okay, so here it's taking lesser time. So here I have shown an example. You can compare it for yourself. See here, what is p? P is given to be a11 plus a22, means this element plus this element, and into b11 plus b22, this element plus this element. So we are adding two elements, 2 plus 4, okay, into 1 plus 4. Okay, that is 30. Like that, similarly we'll find out for all of these, and then we'll apply these formulas. Okay, we'll apply these formulas to get c11 till c22. Okay, so we'll be doing the same thing here. Okay, and getting the final result. You can compare this for yourself. For example, if I compare the answer, I'll compare for 1 16. Okay, how we will get 16? See here, by multiplying this row and this column. 2 2s are 4, 3 4s are 12, 4 plus 12 is 16. So there we got as 16, right? So this is the correct answer, and by using Strassen's matrix multiplication, we can find out the answer in much more less time complexity than traditional method. Okay, it looks more tedious for us, but for the computer it is easier than the traditional method, because in the Strassen's method 7 times we are multiplying, while in the traditional method 8 times we are multiplying. Okay, so this is easier for the computer time complexity. Okay, so time complexity will be, so what will be the time complexity? Here it will be 7 times multiplication, so it will be 7 times t of n by 2. When we do that, we'll obtain the time complexity as theta of n power 2.81. Okay, so traditional method was n cube, this is n power 2.81, slightly lesser value, but when you take larger values of n, it will be having a very great difference. Okay, and let's move on to the next topic. In this topic, we'll be looking at some advantages and disadvantages of divide and conquer. So the first advantage is parallelism. Parallelism means this is the main method. So when we'll divide into two parts and further parts, at that time each part can be executed parallelly, means at the same time it can be executed. Okay, these all can be executed at the same time, and then these both, and then this is the final answer. So in that case the parallelism works a lot. Okay, second is cache performance. See, each algorithm will have the same technique, right? So cache performance, what it will do, it will save the algorithm once for one statement, and it will apply for the other statements also. Okay, and by dividing a main problem into many sub parts, we can find out the solution for difficult problems like Tower of Hanoi and all in a very easy manner. Okay, and it helps in finding out the other efficient algorithms. Means the quick sort and the merge sort was developed by comparing this divide and conquer method. I mean, when the people were observing the divide and conquer method, at that time these two algorithms were developed. Okay, and coming to disadvantages, the first one is recursion is slow. So if you are considering very large elements, at that time recursion can be very slow. Okay, so at that time it's not much useful to use divide and conquer. And sometimes simple problem can be solved by using iterative method, but if you use recursive method, it takes a lot of time. An example can be finding the factorial. Okay, if you use iterative approach, it will be taking very less time than if you take recursive approach. Okay, and Fibonacci also, Fibonacci series. And the third one is repeated solving of the same problem. So it can cause more time, because when you are solving this problem, each of these problem will be having same technique. So when you solve each of this, you are repeating the same steps again and again. So that's a disadvantage that can be overcome by using a technique called memorization. In that, the cache will remember what technique you have applied and will apply to all the other steps. Okay, by using the technique, this disadvantage can be overcome to a particular limit. Okay, to decrease and conquer approach, we'll have the multiple elements here, and for each iteration we'll be eliminating one element or multiple elements, and we'll be solving the rest of the elements. Okay, so there are three major variations. The first one is decrease by a constant. So in insertion sort, first we'll have all these elements in unsorted array, and for each iteration one of the element will be sorted in the first position. Then in the second iteration, two elements will be sorted. So in each iteration, what's happening, the level of the number of elements is decreasing by one value. Okay, so in that way, finally all the elements will be sorted, and this is the approach where the each iteration reduces by a factor of n minus 1. Okay, so that's the first one, which is decrease by a constant. Second one is decrease by a factor. Factor means in binary search, if you consider, we are dividing the array into two parts, so the factor is divided by 2. Okay, so for each iteration it gets divided by n by 2, so it's decreased by a factor. Third one is decreased by a variable. In this, you can consider the algorithm of Euclid. In Euclid's algorithm, the GCD is calculated by n comma m mod n, means whatever be the remainder of m mod n, that will be considered as n, and then n will be considered here. Okay, so the greater the remainder is, the greater the elimination will happen. Okay, so each iteration decreases by a factor of m mod n. Okay, so if this value is more, means if remainder is more, at that time will decrease more, or else the reduction will be lesser. Okay, so this is the third variation, which is decreased by a variable. This is the last one, which is topological sort. In this, we have considered an example. In topological sort, if there are 5 courses, okay, and one student should select one course in each semester. So what will be the case? And there are prerequisites, means you can't take the course C3 unless you have completed C1 or C2. And you can't take the course C4 unless you have completed C3 and C1 or C2. Like that, the arrows are being made, and C5 should be the last course to be taken. Okay, unless you have completed C4, C3, C1 or C2, you can't take C5. So in that way, what is the best order in which the student can take the courses? Okay, so for that we'll be using topological sort. So by using the DFS method and decrease and conquer approach, you can solve. First, DFS. In DFS, what will be the thing? First, start from the main source, go here. Then next one, where you can go C4 and C5, but if you go directly to C5, you will miss out C4. So what you will do, first you will go to C4, then C5. So this is the order, either choose C1 or C2 in the first iteration, and in the remaining iteration C3, C4 and C5. So that's by DFS method. And second one is decrease and conquer technique. In this technique, first find out the source code, source node. Source node means the node which has no incoming node, only it has outgoing node. For example, C1 and C2 are the source nodes. Remove them. After removing them, you will have the source code as, in first iteration you will remove C1, so you will have source code as C2. Remove the source node C2, you will have C3 here. C3 also you remove, at that time you will have C4 and C5. Among C4 and C5, the source node is C4. When you remove C4, you will be remaining with C5. So the order in which we remove the nodes will give us the topological order solution. Okay, this is also known as the source removal method. Okay.